Okay. Right. All right. Round will start. Can you confirm whether I am clearly audible and visible? Let me run again also. Okay, it's very fine, right? Okay, for me it's fine. For me it's fine. And so I think it's okay. If anything, it's very well. Okay. If anything, just let me know. Okay, right. Then we'll start. Right, listen. So last week we couldn't do the class because of a power cut, no? Right? So from the last week, what we have remaining is the other types of questions from wave phenomena, right? So according to the plan, today I'll be starting Doppler's effect, right? And we'll be allocating another separate session for that question discussion about wave phenomena, on wave phenomena, right? I think there are only 6, 7 questions remaining from that period, right? For that 6 or 7 questions, or the whatever the number of remaining questions, I'll be allocating another separate different session. So today we'll be starting Doppler's effect according to the plan. So don't worry, I'll be covering those remaining questions with a separate session, right? Okay, then we'll start. We'll start. Right. So seems everything is fine. Right. So we are now moving on to the next part of waves. Right. Now about oscillations and waves, we have started from oscillations, right, where we have finished simple harmonic motion, right? That is what we had in oscillations, right? And now in the last 2 weeks, we have been doing wave phenomena, right? In wave phenomena, we have discussed about 5 wave phenomena, starting from reflection, diffraction, interference, polarization, right? 5 wave phenomena. And now we are moving on to the next part in waves, right? The next part in waves, that is called Doppler's effect, right? The other two main parts coming up under waves is going to be Doppler's effect and intensity levels, right? So both will be covered during the month of July, right? During the month of July, and by the end of July, right? We'll be stepping into optics as well, right? So now lessons are also going on, right? Lessons are going on, right? And 26 batch is now just 5 weeks from the exam, right? You are like 57 weeks from the exam, right? So every one of us are getting closer to the exam day by day, right? So things are happening around, and now uh, even as the 27 batch, you don't have any like uh, lesser types as you had in the last year, right? Because now you are going to be the senior batch just after 5 weeks, right? You are going to be the senior batch. You are going to be the senior batch, right? So being senior batch means that is not just that title, right? That is responsibility. Responsibility means you are uh, getting closer to the exam, right? Getting closer to the exam now. 28 is still treated as a junior batch, but you will be graduated to the senior batch, right? So have a plan always. Have a plan always when you are working during this time coming up or the time remaining, right? So otherwise, when it comes to A levels, this is not an overnight result, right? That is not an overnight result. In last year also, you have listened to the speeches of students, right? The district rankers, those ones, right? So you know how they have worked. So have that idea and always adjust your plans, right? Adjust your plans and have a proper plan for the coming year, right? Now it's basically a year remaining. Okay, so we'll start without further ado. Heading Doppler's effect. Doppler's effect. Doppler. Doppler's effect. Doppler's effect. Right. Listen now. Listen. The kind of a very special and a unique thing that is kind of different. Right? There are similarities, kind of different from what we have done so far. And real world applications. Right? This plays a huge role, a major role in the real world. Right? Doppler's effect means something like this. Right? So when it comes to Doppler's language or Doppler's jargon, right? There are two important parties, two special parties you have to look into, right? One is called the source, right? Just listen to these words. One is called the source, right? Source means the one who is going to emit sounds, right? The one who is going to emit sounds, right? Sound emit करने का नाम the one who is going to emit sound or emit frequency. Sound means sound of frequency, right? That is called source, right? As the word says, that is source. And there should be someone who is listening to that sound, right? There should be someone who is listening to that sound. Listener, right? Listener. Listener we call the observer, right? We don't use the word listener as a technical term, we use observer, right? The listener is called the observer, right? Source is denoted by S here onwards, right? Denoted by S here onwards. And observer is denoted by O here onwards. Observer is denoted by O here onwards, right? And Doppler's effect is something like this. Listen very carefully, right? The whole idea. Doppler's effect is something like this. When there's a relative motion, what is a relative motion? Relative motion means, right? Relative motion means if any party, any one from source or observer has a relative motion, which means if someone moves or travels with respect to the other party, relative motion. The easiest way to identify relative motion is distance between two objects, right? Two bodies should be changing over time. That's the easiest way to identify relative motion. In mechanics also, we have got the idea about relative motion. The easiest way to identify relative motion is there should be a changing distance in between, right? Maybe two or three objects or any number of objects. The distance in between changes over time, that is called relative motion, right? Then, as an example, even though both objects are moving with say 10 ms minus 1 velocities to the same direction, right? 10 ms minus 1 to the same direction, there's no change in the distance or the gap in between over time, no? Then there's no relative motion, right? So even though there's a motion, there is not a relative motion, right? Such cases are there. So always for the relative motion, the thing is the distance between source and observer. Distance between source and observer should be changing over time, should be changing with time, right? Then if the source and observer, right? If source or observer basically has a relative motion, right? Has a relative motion, the phenomenon of hearing a different frequency from the actual frequency, right? Let's say actual frequency of the source is F. Listen, let's say actual frequency of the source is F. Actual frequency of the source is F, right? The phenomenon of hearing a different frequency. Phenomenon of hearing a different frequency from the actual frequency, right? Which means the actual frequency is not heard by the observer. Observer is hearing a different frequency, a changed frequency, right? Because of this relative motion, right? Now, let's say that frequency is F dash. Let's say that frequency is F dash, right? In Doppler's jargon, we call this the actual frequency or the real frequency. This is called actual or real frequency in Doppler's jargon. Actual or real frequency. And the frequency heard by the observer is called the apparent frequency, right? That is called the apparent frequency. Apparent means that is not the reality. Apparent frequency, right? Apparent frequency. Apparent means that is not the reality. That is not the reality. That is not the reality, right? So what is heard by the observer is something apparent. Something apparent means that is a different frequency from the actual frequency, right? This phenomenon is called the Doppler's effect, right? Now I gave you several keywords, right? I gave you several keywords. We have to know all the keywords when you are stepping into Doppler's effect, right? One is source, right? The observer, then actual frequency and apparent frequency. So simply again, what Doppler's effect means is, right, the phenomenon of hearing a different frequency. The phenomenon of hearing a different frequency by the observer when there's a relative motion between the source and observer, right? So basic idea is that, right? So we'll see how it happens with the equations, numbers, everything, right? And let's see how it goes, right? Now under Doppler's effect, first write this down. Don't take this down. First write down what I say here. Under Doppler's effect, write down the phenomenon of 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 hearing a different frequency. 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 A different frequency from actual frequency. Different frequency from actual frequency. The phenomenon of hearing a different frequency from actual frequency. From actual frequency. When there's a relative motion, when there's a relative motion, when there's a relative motion, when there's a relative motion between, when there's a relative motion between, when there's a relative motion between an observer and source. An observer and source. An observer and source. An observer and source is called Doppler's effect. Is called Doppler's effect. Is called Doppler's effect. Is called Doppler's effect. Right, listen. So when it comes to Doppler's effect, right, this is contributing waves essay question very popularly, very frequently, right? For whole 30 marks, Doppler's effect questions are coming, right? Now, as a part, Doppler's effect is a comparatively small part, right? Comparatively smaller part, but yet it contributes all 30 marks of essay in essay questions, right? In waves essay question contributes for all 30 marks, right? So when it comes to scoring in that particular question, right, Doppler's effect is a very convenient and an easy part we have when it comes to scoring, right? So keep that in mind from the beginning and grab it at once. Then this is actually a small and a convenient and an easy part, right? Easy part, but when you are familiar with everything from the beginning, there's nothing here, right? So otherwise, if you try to do this like here and there, right, it is not going to connect everything, right? Because it has connections. Everything has a flow. Right? So that's the thing. So grab it from the beginning, from today, from scratch. Then if an essay from Doppler's effect comes, right, easily you can score. Right? Okay. Then, right. Listen. From that definition, from that introduction, highlight these terms. I like to underline these phrases. Phrases. First one is hearing a different frequency. First phrase, hearing a different frequency. Underline or highlight hearing a different frequency. Underline or highlight hearing a different frequency. Hearing hearing a different frequency. Underline or highlight, hearing a different frequency. Then underline or highlight, relative motion. Relative motion. Relative motion. Then relative motion. Relative motion. And then source and observer. And then source and observer. Source and observer. Source and observer. Right? So those are the keywords here. Keywords, jargon, the Doppler's language. Right, listen. Listen. Then the next most important thing. Now it says clearly says that when there's a relative motion only, Doppler's effect occurs, which means having a relative motion between source and observer is mandatory. Right? That is compulsory for Doppler's effect. Right? If there's no relative motion, there's no Doppler's effect. Right? So having a relative motion is mandatory. Right. Next point, mention using a red pen. Next point, mention using a red pen. To occur Doppler's effect. 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 A relative motion between. A relative motion between. To occur Doppler's effect. To occur Doppler's effect. A relative motion between. To occur Doppler's effect. A relative motion between. To occur Doppler's effect. A relative motion between source and observer. A relative motion between source and observer. A relative motion between source and observer is compulsory. A relative motion between source and observer is compulsory. A relative motion between source and observer is compulsory. Is compulsory. A relative motion between source and observer is compulsory. Put a comma and write down. Put a comma means put a comma and keep writing. Therefore, the distance between. Therefore, the distance between source and observer, distance between source and observer should be changing. Distance between source and observer should be changing over time. The distance between source and observer should be changing over time. Distance between source and observer should be changing over time. Should be changing over time. Right? Should be changing over time. Right. As the next heading, write down equation of Doppler's effect. Write down equation of Doppler's effect. Equation of Doppler's effect. Equation of Doppler's effect. Right. Listen. Equation of Doppler's effect. Right. This equation is for the apparent frequency. See? And we have to keep this equation in mind. Right? Apparent frequency is usually denoted by f dash. Right? This is the equation. Listen. Here, sound velocity through air. Sound velocity. Look at the word. Sound velocity through air. Through air with respect to observer. With respect to, this is all about relative motion. That's why these terms are with respect to observer. With respect to observer over over sound velocity through air. Don't write, just look at here. Sound velocity through air with respect to source. With respect to source. Whole thing into real frequency. That is usually denoted by F. Right? This is called the equation of Doppler's effect. Right? We don't have the proof of this equation here in L-Earth, right? So what we'll be doing is we'll be using the equation for the applications, right? Now we have to keep it in mind, because always when you are writing, when you are answering essays, right? First thing you have to mention the equation, right? After mentioning the equation only, you can approach, right? Kind of a lengthy equation, right? Have to keep in mind apparent frequency equals sound velocity through air with respect to observer, right? Observer over sound velocity through air with respect to source. Observer source DNA, that is sound velocity through air into real frequency. Right? Take it out and highlight it. Take it out and write out. Right? Right? Now moving forward, listen, moving forward, this is only equation you have to keep in mind, right? Otherwise, another point that most of the students are kind of misleaded and misguided is, right? We will be proving some standard scenarios in the coming part, right? We'll be proving the phenomenon of Doppler's effect or the impact of Doppler's effect for some standard scenarios, right? Some students think that we have to keep those equations in mind. We'll be proving for 7 standard scenarios, right? No need to keep anything in mind, right? Only equation you have to keep in mind moving forward is this, right? Only one equation is here in Doppler's effect, right? There's only one equation. The whole lesson relies on this equation, right? This whole lesson relies on this equation only, right? Then for is, right, we are writing this equation as, right, f dash equals, right, f dash equals abbreviated terms sound velocity through air, just abbreviated terms are through air with respect to observer over sound velocity through air with respect to source into f means FPL, right? Just for the is, sometimes we'll be writing this like this as well, right? Always writing means it will be writing this, right? And when you are using it repeatedly, right, then you can use this, right? That's why the story, right? Nothing here, just an abbreviated term. So that's it. Listen. Now, there's a very important and main observation here. That is this depends only on velocities, no? See, sound velocity through air with respect to observer. Sound velocity through air with respect to observer. That is a velocity, no? That's a velocity, right? Sound velocity, that's a velocity, right? This is also sound velocity through air with respect to source. That is also velocity, right? It depends only on velocities. It depends only on velocities, right? Another point. Most of the students are again messing up is right. So we know having a changing distance between source and observer is mandatory for Doppler's effect. No? That is mandatory, right? No doubt about that. That is mandatory, right? But very important, magnitude of Doppler's effect, right, or the magnitude of apparent frequency is never going to depend on distance, right? That never depends on distance. That is mandatory. But the magnitude doesn't depend on distance. It depends only on velocities. It depends only on velocities. Right? Write down below with the red pen. Write down below with the red pen. Write down below with the red pen. Doppler's effect. Doppler's effect. Slash apparent frequency. Doppler's effect. Slash apparent frequency. Doppler's effect. Doppler's effect. Slash apparent frequency. Doppler's effect slash apparent frequency. Apparent frequency. Doppler's effect slash apparent frequency. Apparent frequency depends only on velocities. 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 And it does not depend on. 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 And it does not depend on distance. And it does not depend on distance. Does not depend on distance. Right, within brackets write down independent of distance. Within brackets, independent of distance. Within brackets, independent of distance. Independent of distance. Independent of distance. Right, listen. Right, listen. These are the core things, heart of Doppler's effect. Right, we'll be mentioning all these points in red. Right, these are the all points you have to take forward, carry forward. In Doppler's effect. Right, listen. The other thing, when we apply this equation, listen, when we apply this equation, we can apply this equation only along the connecting line between source and observer. Right? We can apply this equation only along the connecting line. Only along the connecting line between source and observer. Right? Only along the connecting line between source and observer. Next point. Write down in red. Doppler's equation. Doppler's equation. Doppler's equation. Doppler's equation. Doppler's equation is applicable. Doppler's equation is applicable. Doppler's equation. Doppler's equation is applicable. Doppler's equation is applicable. Doppler's equation is applicable only along. Doppler's equation is applicable only along the connecting line. Only along the connecting line. Only along the connecting line. Connecting line, no? Only along the connecting line. Only along the connecting line between source and observer. Only along the connecting line between source and observer. Only along the connecting line between source and observer. Only along the connecting line between source and observer. Only along the connecting line between source and observer. Right? Now, as an example, it's like this. Let's say the source is something like this. Right? Say the source is something like this. Right? And say observer A is here and observer B is here. Right? So when you apply Doppler's effect, like you can apply Doppler's effect either along the connecting line between A and B or along the connecting line between A and B, S and A and S and B, like this. Right? Like this. Can be applied only along the connecting line. Only along the connecting line. Right? Take it down. And at once we can apply it for one observer, right? Now, just to show you, I have drawn here two observers. Right? Otherwise, when we apply the equation, there's only one observer in the equation. See? One observer in the equation, right? Only one observer and one source at once. Right. Take down. Right. Right. Then below. Okay, use red. If there are no velocities, use red. If there are no velocities, 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 acting along the connecting line. If there are no velocities acting along the connecting line, there are no velocities acting along the connecting line. There are no velocities acting along the connecting line. There are no velocities acting along the connecting line. There are no velocities acting along the connecting line. There's no Doppler's effect. 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 Listen. If there's no Doppler's effect, according to the definitions, tell me what is going to happen if there's no Doppler's effect. What is going to happen if there's no Doppler's effect? You can go through definitions again and understand and give me an answer. What is going to happen if there's no Doppler's effect? What basically I'm asking is whether no sound is heard, no frequency is heard, no sound is heard, or the same sound is heard, or what's happening, right? That's what I'm asking basically. If there's no Doppler's effect, what's the thing? What's happening? Any doubts? Listen. Doppler's effect is the phenomenon of hearing a different frequency, right? That's the point. Doppler's effect is the phenomenon of hearing a different frequency. Doppler's effect is a phenomenon of hearing a different frequency. Right? That's a phenomenon of hearing a different frequency. Then, if no Doppler's effect, no different frequency is heard. If no different frequency is heard, which means same frequency is heard by the observer. Right? That is all about hearing a different frequency. Right? If there is no Doppler's effect, right? There is no Doppler's effect, still the sound is heard, frequency is heard, but no difference. No difference. Then same actual, same real frequency will be heard. Same actual or same real frequency will be heard. Right? That's the whole idea. That's the whole idea. Sound now, there should be some disability in the ear of that observer. Right? In the ears of observer. Hearing disability unless otherwise, sound is heard. Sound is heard. Because what Doppler's determines is that is about the different frequency. That's it. Right? Difference है ताने दे. Right, then again, write down below with the red pen. Keep using the red pen. Right, with the red pen, write down. Keep using the red pen. Write down below. The actual frequency is heard by observer. 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 Actual frequency is heard by observer. If there is no Doppler's effect. The actual frequency is heard by observer if there is no Doppler's effect. Actual frequency is heard by observer if there is no Doppler's effect. Right. So it doesn't mean no sound is heard. Always actual frequency is heard. Right. If there is no Doppler's effect. Right. Listen. Next. Next. Okay. These things from reading in a relaxed manner. This is a small lesson, right? Comparatively a small lesson, right? And as I told you, yet the contribution is higher. Right? Always one MCQ is there. Definitely one MCQ is there. But other than that, when the essay comes, it comes from 430 marks. That's the main benefit of this. When an essay comes from Doppler's, right? Then next heading, Mach number. Next heading, Mach number. Mach number. Right? Mach number. Some pronounce the same as Mach number also. Right? Some people pronounce the same thing as Mach number also. Right? But more popular pronunciation here is Mach number. CH, Mach. Right? CH is Mach. But I have heard some people also pronounce this as Mach number also. So just know both and don't worry about whether it's Mach or Mach. The popular pronunciation is Mach. Right? Popular one is Mach. Right? But maybe because of some translation errors or something like that. Right? Because the word Mach is coming from a different language. Right? So therefore, because of these of the translation errors or differences, right, can be also pronounced as Mach number also. So it's called Mach number. Right, Mach number. Mach number means this. Listen. Mach number means this is a ratio. Right? Mach number is the ratio between velocity of an object velocity of object to velocity of object to velocity of sound. Velocity of object to velocity of sound. Sound means sound through air. Velocity of object to velocity of sound. Velocity of sound to air. This ratio is called Mach number. This ratio is called Mach number. Listen. Listen, this ratio is called Mach number. Right? Which means, right? If an object has a velocity which is less than velocity of sound through air. By the way, what's the value of the average value? General value of the average value of velocity of sound through air? What's the average value, general value of velocity of sound through air? What's the general value, average value? Velocity of sound through air. General value 340. Right? 340. It varies from 320 to 340. Right? The general value of sound through air is 340 ms minus 1. Right? Common sense and general knowledge. Right? What is the speed of light through vacuum? Velocity of light through vacuum? 3 times 10 to the power 8. 3 times 10 to the power 8. So likewise, those general values, common values, we have to have an idea, right? Rough idea, that's always better. Velocity of light is 3 times 10 to the power 8. Velocity of sound is 340, right? Likewise. Now, if an object has a velocity lesser than velocity of sound, right? Its Mach number is less than 1, right? So in any case, if velocity of the object is equal to velocity of sound, such objects are there, such cases are there, right? Then Mach number equals 1. If there is greater cases are also there. If there is greater than velocity of sound, there is a scenario where Mach number is greater than 1, right? The reason to introduce Mach number is to us to easily separate and segregate between these scenarios, right? You will see how it affects, and how it breaks down into Doppler's effect and the other things coming up in terms of Mach number. The whole purpose of introducing Mach number is of segregation. Categories. Categorize करना हमारे ने वाले दिए. Right? To categorize these objects, whether Mach number is 0, less than 1, equals 1, greater than 1. Likewise, now we can easily categorize using for the base on Mach number. Right? Take out the equation and highlight it. Take out the equation and highlight it. Right? How will I join? Can anyone tell me how many pages I should? Can someone tell how many pages we have Done so far. If I said it private, that's all fine. Fine, I just said, since I didn't see a response in the maker. Right? Okay. Then write below with the red pen. Below the equation with the red pen. Write down. Below the equation with the red pen. Write down below the equation with the red pen. The plus equation. The plus equation. The plus equation. The plus equation is applicable. The plus equation is applicable. The plus equation is applicable. Only when the plus equation is applicable only when the plus equation is applicable only when the plus equation is applicable only when Mach number is less than 1. The plus equation is applicable only when Mach number is less than 1. The plus equation is applicable only when Mach number is less than 1. The plus equation is applicable only when Mach number is less than 1. Right. Listen. Now, from the things you have learned so far, from the things you have learned so far, right? So far, right? Not a big deal. We have only one equation, right? And you know few other things about Doppler's equation, Doppler's effect, right? It depends on velocities, independent of distances, but having a relative motion is mandatory. So having a change in distance in between source and observer is mandatory, even though the magnitude doesn't depend on the distance, right? And Doppler's equation is applicable only along the connecting line between source and observer, right? The phenomenon of hearing a different frequency is Doppler's effect. If they ask no Doppler's effect, the real frequency, actual frequency is going to be heard, right? So likewise, now we know a few facts, right? Now using these facts, we are going to prove some standard scenarios, right? Standard scenarios when hearing Doppler's effect, right? So there are like 7 scenarios altogether, right? We'll be starting one by one, and I'll be explaining the first one, no, first two, then we'll let you do, right? Okay, then write down, write down, write down as an example, write down as an example, write down as an example. Determine as an example, example, determine, right? Write down, determine apparent frequency, determine apparent frequency, determine apparent frequency, determine apparent frequency, determine apparent frequency due to Doppler's effect, apparent frequency due to Doppler's effect, apparent frequency due to Doppler's effect, apparent frequency due to Doppler's effect. The following scenarios given below. In 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 the following scenarios given below. within brackets, within brackets, within brackets, consider, within brackets, consider velocity of sound through air. Consider velocity of sound through air as v. 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 Velocity of sound through air as v. Okay, right, listen. I'll be doing this under 7 different scenarios, right? So we'll be doing one by one. As scenario 1, write down. First one. Scenario 1, write down. Right? Scenario 1, number 1, write down. Write down when an observer travels. Likewise, write the scenario. When an observer travels. When an observer travels. Observer travels towards a stationary source with the velocity u. When an observer travels towards a stationary source with the velocity, when an observer travels towards the stationary source, with the velocity u, Right, listen now. Listen. So this is the first idea, right? So I'll explain the first one from 0, right? We'll explain the first one from 0, right? And then gradually I'll be letting you do the other scenarios coming up, right? Always when a scenario is given, right? Have a sketch, right? First thing is have a sketch, right? When an observer travels towards a stationary source, right? For source, I'm going to use a speaker, right? For source, graphically represent the source, I'm going to use a speaker, right? And to represent the observer, I'll be using some kind of a sketch of a person like this. See? Now let's say the source is here. Let's say the source is here. See? Let's say the source is here. Right? And always assume frequency of the source as f. Right? Always assume the frequency of the source as f. Real frequency, yeah? Real frequency of the source is f. And it's a stationary source, no? Stationary source. Then velocity of the source equals 0. Right? Then velocity of the source equals 0. And we have an observer. Right? This is the source. Right? This is the observer. An observer travels towards the source with velocity u. Right? Now it travels towards the source with velocity u. Travels towards the source with velocity u. Right? We know Doppler's effect is applicable only along the connecting line between source and observer. Then first thing, draw the connecting line. Draw the connecting line like this. Right. And then we know to apply in Doppler's equation, we need relative velocities, not just velocities. We need relative velocities. Right now, when we find relative velocities, we are not going to apply the principle of relative velocities, right? And find the velocity, right? We know how to find it easily when it comes to relative velocities, right? Quickly, we have done in mechanics and in the paper class also, right? Like in weekly basis, I was putting relative motion questions also because now these days means now in the modern questions there's a like high probability of questions towards relative velocities, relative motion, right? So in the paper class also, in like almost all the papers we had questions from relative velocities, right? So I have explained the same in those things also, right? I will quickly recall. without applying principle, right? We can get relative velocities like this if needed, right? When objects travel in the same direction, say A and B, when objects travel in the same direction, say these velocities are say V1 and V2, right? If these velocities are V1 and V2, the idea is this. Say I need velocity of A with respect to B. I need velocity of A with respect to B. What's it? Velocity of A with respect to B. With respect to means if that particular frame, that reference frame is at rest. Right? With respect to means if there is at rest. Now B is moving in this frame. B is moving. Since B is moving in this frame, right? We have to consider the frame where B is at rest. To make him rest, apply an opposite velocity to make him rest. See, when we apply velocities to a frame, for each and every object in the frame, velocity will be applied, right? And this applied velocity is called the relative velocity. Applied velocity is called the relative velocity. Listen, now if you simplify these resultants, the relative velocity comes. Now we need velocity of A with respect to B now. Velocity of A with respect to B is now V1 minus V2. Likewise, easily we can find this out using this V1 minus V2 without applying the principle. Now, in this frame, velocity of B with respect to B is V2 minus V2 0. In this frame, velocity of B with respect to B is 0. Velocity of A with respect to B is V1 minus V2. So simply, when objects are traveling in the same direction always subtraction comes. If they travel in opposite directions, addition comes, right? So simply what we do is this, right? If you need to find the relative velocity for an object, make him rest, right? When you apply a velocity to make him rest, right? That same velocity should be applied for each and every object, each and every body in the reference frame, right? Then if you simplify the velocity as a result, then relative velocity comes, right? Now here also we are going to use the same, right? Look at here, right? This idea is clear now. Just recall before going here, right? Listen. Right now, this is already at rest, right? This is moving with the velocity u. Right. The other thing is marking velocity of sound, because in Doppler's equation what we have is velocity of sound with respect to observer, right? Or sound velocity through air with respect to observer, or sound velocity through air with respect to source. So we need to consider sound velocity with respect to source or observer. Then the next most important thing is knowing the direction of sound velocity, right? Very simple. This is the idea. Direction of sound velocity is direction of the ear of the observer. Listen carefully again, right? Direction of sound is direction of ear of the observer. As an example, right? Say you are sitting here, and you are hearing my sound, you are hearing my voice, right? So how you are hearing my voice is the voice is coming out from the mouth, and that sound wave propagates towards air medium to your seat, to your ear, right? And when you get that sound wave to your ear only, you are going to hear it, right? So therefore, simply, if you are hearing something, which means sound wave is propagating towards, right? It's coming into your ear, right? Kannada sound එක කාවොත් විතරයි, kannada sound wave එක කාවොත් විතරයි අපිට sound එකක් ඇහෙන්නේ, right? So if you got a sound wave into your ear only, we are going to hear a sound, right? Now observer is hearing this, right? To hear this by observer, sound velocity should be towards the ear of the observer, right? We usually mark sound velocity like this because that's a wave, no? Since that's a wave, right? We usually mark it like this. Direction is towards the observer, right? Listen. Now about finding relative velocities. To find relative velocity, right? you have to apply velocities and make that particular body rest, right? As I explained before. Whether I explained right now, this has no velocity, then it is already at rest. No need to apply, no need to consider relative velocity because that is already at rest. But this one is not at rest, then relative velocity will be considered. Relative velocity should be considered. Then relative velocity of this u is opposite u opposite, and circling. Circling is a standard. Listen. Circling is a standard. If we don't apply the principle, right? If we don't apply the principle, the graphical representation of relative velocity is circle, right? If you have circled velocities, which means you have considered relative velocities, right? Standard, right? Don't circle anything and everything as you prefer. There's a standard behind circling. Right. If you have circled something, a velocity, something like if you have circled a velocity, which means you have considered relative velocity. No need to write anything in words. Right? No need to write anything in words. No need to mention anything in words. Right? That's a standard. Right? Then I have considered relative velocities. Okay. Now we are applying the equation. Right? So until you keep this equation in mind, until you are able to recall, memorize the equation, right? You always better write this equation in words. You always better to write this equation in words, right? Then apparent frequency equals sig f dash. Apparent frequency equals sound velocity through air. Sound velocity. This is the equation. Sound velocity through air with respect to observer over sound velocity through air with respect to source times real frequency. Right? See how this is applied. Now we need f dash. F dash is going to be heard by the observer. Then f dash is here, going to be heard by the observer. F dash equals, listen, sound velocity through air with respect to observer. Then sound velocity through air is leftwards. Listen, sound velocity through air is leftwards. With respect to observer, relative velocity of observer is u to the leftward direction. Right? Then relative velocity is v plus u. Once you found the relative velocities, no need to check the original velocities again. Right? Because this whole thing is based on relative velocities. Once you found the relative velocities, no need to check the real velocities or the actual velocities again, original velocities again. Right? Now, sound velocity through air, this one, with respect to observer, then relative velocity of observer is u to the left, then v and u to the left, v plus u. Then v plus u comes here. Right? Then here, sound velocity through air with respect to source. Source is at rest. With respect to source is at rest. If source is at rest, right? There's no relative velocity for this one. Then sound velocity through air with respect to source is v minus 0. No need to write 0. It's just v. Right? If someone is at rest in that reference frame, then only sound velocity through air comes. And it's just v. Right? Into real frequency. Real frequency is considered as f. Right? So this is called the apparent frequency heard by the observer now. Right. Checking this answer, tell me whether the observer is hearing a frequency greater than real frequency or an apparent frequency less than real frequency. What about it? Is it an apparent frequency greater than real or less than real? Apparent frequency is v plus u or v into f. Less than or greater than? What about f dash? Check with the equation. Right? It's greater because this v plus u. V plus u is, right, something added to v. So that's a term greater than v. Then a greater term over v. Greater term over lesser term. This is a ratio greater than 1. right? Then a higher frequency, a greater frequency is going to be heard. Right now, in this case, right, f dash is greater than f. F dash is greater than f. Right? F dash is greater than f. Right? That is how apparent frequency is found is determined using Doppler's effect. Right? So likewise, you'll be practicing uh, seven standard scenarios, right? Seven standard scenarios doesn't mean you have to keep these equations in mind, no. Right? It is just for the sake of practicing this, right? Otherwise, no need to keep these equations in mind. මේ equations මග තිබ්බ කියලා ගණන් හදන්න බෑ. Simple as that. Right? මේ equation මග තියාගත්ත කියලා ගණන් හදන්න බෑ. ඉතින් වැඩක් නැහැ. Right? Only equation you have to memorize is this one. General equation of Doppler's effect. That's it. වෙන මොකුත් ඕනේ නැහැ. Right? Okay, raise your hand if clear enough. Raise your hand if clear enough. And ask if any questions. Anything to clarify? Is there anything? Right. So if no questions, take it down. If no questions, take it down. Right, take it down with the understanding because after this scenario, right? After this scenario, you have to do these scenarios by your own. Do the next scenarios, coming up scenarios by your own. Right? So do it with the understanding. Do it with the understanding. But take it down with the understanding. But understanding is the thing here. Okay, right. Okay. Then if no questions, right? Any questions? Mention this also, but dash is greater than f, which means now uh, imagine the scenario in reality, right? Now someone is traveling towards the source at rest, right? So always when we travel towards the source at rest, right? Both frequency and loudness increases. Loudness and frequency are two different things, right? But both behave the same manner. You better memorize that way for the ease of memorizing. Right? Otherwise, these two are two different things. Our frequency means that's a number of vibrations per second. Loudness is about amplitude, right? Both loudness and amplitude increases. Now, as an example, say you are moving towards a siren, right? A siren is kept somewhere at rest, and we are traveling towards the siren. We are traveling towards the siren, right? So when we travel towards the siren, right, we'll hear higher loudness now. So at the same time, we'll hear higher frequency also, right? That's the idea here. Higher loudness, higher frequency, right? Yeah, right? Higher loudness, higher frequency. Okay, then shall we go to scenario two? Then write down scenario two. Write down this way. Scenario two. Write down. No? Write down. Scenario two. Write down. When an observer travels. Write down. When an observer travels. When an observer travels away from a stationary source. When an observer travels away from a stationary source. When an observer travels away. When an observer travels away from a stationary source. When an observer travels away from a stationary source. With the velocity u. When an observer travels away from when an observer travels away from a stationary source with the velocity u. Away from a stationary source with the velocity u. Right. Try now and send your answers. Try and send your answers. Right. Try now and send your answers. Right. Have the sketch. Do everything we have done here. Right. Do everything we have done here so far. Right. Do everything we have done here so far. All right, finished. Okay, finished. We have got answers. P minus U over V. Right. See, then when an observer travels away from this stationary source. Right. Now, say source is here. Right. Check your working again. Source and the observer. Right. An observer travels away now. Away from the source. Source is stationary. Source is stationary. U equals 0. Right. This is the source. Right. This is the observer. O. Real frequency. F. Current frequency heard by the observer. Safe dash. Right. What the reaction observer towards the ear of the observer in order to hear should be towards the ear of the observer in order to hear. Then connecting line is this. Connecting line is this. Right. Then sound velocity should be towards the observer. V should be towards the observer. Right. And we need relative velocities. This is at rest already. No need to consider relative velocity. This one is not at rest. Then relative velocity is u to the right. Applying the equation. Applying the equation. Dash equals. Right. So again, sound velocity to air. With respect to observer over sound velocity through air with respect to source times real frequency. Right, then dash equals dash equals sound velocity through air with respect to observer. Observer's relative velocity is u to the right and v is to the left. Then with respect to observer, consider v with the relative velocity. V is leftwards and the relative velocity is rightwards. Then v minus u. V minus u over sound velocity with respect to source is at rest. Then only sound velocity comes v. Real frequency. F. This is the final answer. V minus u over v. Right. What about the magnitude now? V minus u is less than v. No? Then this one is heard a lesser frequency than actual frequency. This one has heard a lesser frequency than actual frequency. Right. Now again, an example scenario is if the observer is moving away from a siren, let's say from a horn, no siren, whatever it is, from a siren. The observer is moving away, then loudness decreases. As loudness decreases, right? Similarly, frequency also decreases. Right? Clear enough, right? Make the changes, make your changes. Right? Now we can move on to next scenario. This is scenario 2. This is scenario 2. Right, now let's go to scenario 3. Let's go to scenario 3. Right, check your working. This is applied only along the connecting line. Because these velocities are along this line. Even though I have marked it here, right? Otherwise, if I mark all the velocities on the line, sometimes it looks complex. So that's why otherwise the velocity is on the line. Right? If the object has a velocity, if the observer has a velocity, right? For each and every part of the body, the same velocity is there, then on the line, velocity is on the line. That's why Doppler's effect is applicable. Right? That's why Doppler's effect is applicable. Right? Otherwise, we can't use Doppler's effect. Right? Shall we go to scenario 3? Right? Write down scenario 3. 3, write down. When a source travels, when a source travels, scenario 3, when a source travels, right? Scenario 3, when a source travels towards a stationary observer. When a source travels towards a stationary observer. When a source travels towards a stationary observer. When a source travels towards when a source travels towards a stationary observer. When a source travels towards a stationary observer with a velocity u. Right? When a source travels towards a stationary observer with the velocity u. When a source travels towards a stationary observer with the velocity u. Alan? Right. 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 3 minutes. 4 minutes. Sorry. Three minutes. Right. Do everything we have done before. So everything we have done before. We are getting answers. Okay, we are getting answers. Let's see. Right now, C is at rest. And this one travels. Right now, source travels towards stationary observer. Observer is at rest now. U equals 0. But source travels towards the observer with the velocity u. Right? Now still, the sound is heard by the observer. Right? Still the sound is heard by the observer, then direction of velocity of sound should be towards the observer, towards the ear of the observer. Right? Towards the ear of the observer. Right? Then relative velocity of this one is u to the right, u to the right. Then apply the equation. Right? Apply the equation. Right? Apply the equation. Sound velocity through air with respect to observer. Listen. Sound velocity through air. Sound velocity through air with respect to observer. Now observer is at rest. If observer is at rest, sound velocity through air is same as sound velocity at rest, means no, there's no relative velocity, right? Then just v. Then below sound velocity through air with respect to source, right? Relative velocity of source is u to the right, whereas v is to the left. Then relative velocity with respect to source is v minus u into actual frequency f. This is the answer. Fine. Does it here a greater frequency or lesser frequency? A higher frequency or lesser frequency? V O V minus u. V O V minus u. Right? It's clear that, very clear that V minus u is less than V. V minus u is less than V. Right? V minus something. V minus something. So V minus u is less than V. V minus u is less than V. Since V minus u is less than V, this ratio is greater than 1. So it hears a higher frequency. It hears a higher frequency. In this case, f dash is greater than f. Right? Again, real world scenario is listen, real world scenario is say we are at rest and a siren is coming towards us. Right? A siren is coming towards us. Right? When it comes towards us, we will hear higher loudness at the same time a higher frequency. Right? That's the idea. A higher loudness and at the same time a higher frequency. Higher loudness at the same time a higher frequency. Right? Fair enough, right? Easy, right? Easy. Easy. I'm not kidding. Actually, that's a very manageable, convenient lesson. Right? It says all day metti maarna easy. On the DOPPLER'S school or not. Okay, then. Let's go to scenario 4. Right, go to scenario 4. Scenario 4. Scenario 4. Scenario 4. Right now, scenario 4. When a source travels away from a stationary observer, when a source travels away from a stationary observer. Now you also can guess what to come. Right? Simple scenarios here. Next one. When a source travels away from when a source travels away from a stationary observer, when a source travels away from a stationary observer with a velocity u, with a velocity u, right, right. Okay, finished. Finished, right? Okay. Then the x are opposite. Right? Opposite again. Then this travels away. This travels away. Right? This travels away. Those travels away from the observer. Right? Then relative velocity of the source is leftwards. Right? Again, this is sound velocity to with respect to observer. Observer is at rest. If the observer is at rest, only he comes. Right? And sound velocity to with respect to source. With respect to source, same direction, v plus u. V plus u. Right? V plus u is greater than v. V plus u is greater than v, which means this ratio is less than 1. V plus u is greater than v, no? Since v plus u is greater than v, this ratio is less than 1. The ratio is less than 1. Since the ratio is less than 1, right? It bears one lesser frequency f dash less than f. I always keep it in mind with a real example, with a real world example, right? Practically, if you move out, right? If the source goes out from a stationary observer, right? Up in the source, right? If the source goes out, we hear lesser or lower loudness, no? Right? So as the loudness behaves, frequency also behaves. Right? Saying again, loudness and frequency are two different things, but they behave same. They behave same. Right? Scenario 5. Scenario 5. Scenario 5. Scenario 5. Write down. When an observer, when an observer travels towards a source with velocity u1 and and source travels towards observer with velocity u2, right? An observer travels towards the source with velocity u1. Observer travels towards the source with velocity u1, and the source travels towards observer with velocity u2, right? Right? Sketch again, right? Read it carefully and have the sketch applied. Read it. Right? 3 minutes again. Okay, what about it? What about it? Anyone? V plus U1 over V minus U2. V plus U1 over V minus U2 times Z. Possible answer. Good. Possible answer. Right. Now the diagram is like this. Equation is same anyway. Right? Equation is same. Right. See? Now the observer travels towards source. Observer travels towards source with velocity U1. With U1. Right? And the source travels towards observer with velocity U2. Right? Observer and the source. Connecting line is this. Connecting line is this. Right? So wherever they travel, the sound is heard by the observer. Sound is heard by the observer, then we should be towards the ear of the observer. Right? We should be towards the ear of the observer. Towards the ear of the observer. Right. Now, apply relative velocity. Right, to make him rest, the relative velocity of the observer is U1 to the left. To make the speaker, the source rest, right, relative velocity of the source is U2 to the right. U2 to the right. Right, that's it. Apply the equation. Then f dash equals, right, look at here. Right, check your answers, huh? Check your answers and look at here. Right. Sound velocity through air with respect to observer. Observer is here. Sound velocity through air leftwards. With respect to observer, relative velocity of observer is U1. U1 to the left. Then V plus U1. V plus U1. V plus U1. Right. Then below, sound velocity through air with respect to source. Sound velocity through air leftwards. Right. With respect to source, relative velocity of the source is U2. Relative velocity of the source is U2 to the right. Then V minus U2. V minus U2 into N. And V plus U1 is greater than V minus U2, which is V plus something, this is V minus something. This is a ratio greater than 1. Then F dash is greater than F. F dash is greater than F. And again, always think of a practical scenario. Right? Think of a practical scenario. Right? Siren is moving towards us and we are moving towards the siren. Right? Loudness increases rapidly. Loudness increases rapidly. So frequency also increases. Frequency also increases. Right? Clear? Alright. Then scenario 6. Scenario 6. Let's go to scenario 6. Scenario 6. Scenario 6. Write the same. Write the same as away. Right? Write the same as away. When an observer travels away from when an observer travels away from a source with velocity U1 and source travels away from observer with velocity U2. Replace two words with away from. Right? Scenario 6. Scenario 6. When an observer travels away from a source with velocity U1 and source travels away from observer with velocity U2. Right. 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 See, then say these two are now moving away from each other. Moving away from each other. Right. Moving away from each other. Then observer travels away from this with the velocity u1 and source travels with the velocity u2. Right? So wherever they go, direction of velocity of sound should come to the ear of the observer, should come into the ear of the observer. Right? Then to the ear of the observer, then value velocity for the source is sorry for the observer is u1 to the right, for the source u2 to the left to make it rest. Right? And I'm right. Sound velocity with respect to observer. Observer is here. With respect to observer, sound velocity is leftwards. Observer's relative velocity is rightwards. Then v minus u1. V minus u1 over sound velocity with respect to source, right? Sound velocity v to the left and relative velocity of source is also to the left, right? Then v plus u2. V plus u2 into f. Right? V minus something less than V or V plus something greater than V. This is a ratio less than 1. Ratio less than 1. Then F dash is less than F. F dash is less than F. Dash is less than F. Right? So again, practically argue if we move away from each other, right? Loudness decreases, frequency also decreases. Loudness decreases, frequency also decreases. Right? It's easier to keep in mind when they behave in the same manner, right? It's easier to keep in mind when they behave in the same manner, right? They behave in the same manner. Okay, right? Right. Check if any changes in your working now. Check if any changes, any differences in your working. Right? And then let's go to scenario 7. Scenario 7. Scenario 7. Write down. Scenario 7. Write down. Right now, scenario 7. When an observer travels towards a source with velocity u1 and source travels away from observer with velocity u2. Away from observer with velocity u2. Right, last one. Right. Right. V plus u1 over v plus u2 times f. Good. V plus u1 over v plus u2 times f. Right. See, observer travels towards source. Observer travels towards source. Observer travels towards source with velocity u1 and source travels away from observer with velocity u2. Connecting line is here. Right. Then to hear this sound by the observer, velocity of sound through air should be towards the ear of the observer. Right. Then to make him rest, relative velocity of the source is right. Observer is u1 to the left. For the source, there is u2 to the left. u2 to the left. Right. This is our observer, and this is my source. Right. Real frequency is f. Apparent frequency here is only the test. Right. Apply. Apply. Then f dash equals sound velocity through air with respect to observer. Sound velocity through air with respect to observer. With respect to observer, observer is here. Sound velocity through air leftwards. Relative velocity of observer leftwards, then v plus u1. v plus u1 over sound velocity through air with respect to source. Right? Sound velocity is leftwards with respect to source. Relative velocity of source is also leftwards, then v plus u2. v plus u2 times f. right? Here is the answer. And here we can't say whether it's greater than or less than actual frequency, right? Without knowing the magnitudes of U1 and U2, right? Then the only thing I can say is if U1 greater than U2, see what happens. If U1 greater than U2, then if U1 greater than U2, see, if U1 greater than U2, this term becomes greater. If U1 is greater, if U1 is greater than U2, this term becomes greater, then F dash is greater than F. Right? Or else there are two scenarios now. If U2 is greater than U1, right? If U2 is greater than U1, if U2 is greater, then denominator becomes larger. When denominator is larger, this becomes lesser, then F dash is less than F. Right? So otherwise, without knowing about U1 and U2, we can't say anything about F dash, right? About the magnitude, whether it's less than or greater than F. Right? Mention this way. Right? Finished. So these are all, listen, these are all the standard scenarios, standard occasions we have, right? Standard occasions we have about Doppler's effect, right? But when it comes to questions, that is not limited to these cases, not only limited to these cases, right? There are some modified ones with angles, visual components and angles and there are different ones, right? Not only limited to linear motion also, then we have come across linear motion because they are just standard scenarios to you to give this initial idea to practice this, right? Otherwise, don't expect the same in questions. When it comes to questions, there are like modified cases also. Right? There are modified cases also when it comes to questions. Right? When it comes to questions, there are modified cases also. Right. Before moving on, any questions up to here? Raise your hand if everything is clear enough. And if you are asked if anything, just go through the note from the beginning and ask if anything. If you need to know from the beginning before we move on. Okay, clear, no questions, right? Okay then. If no questions, right, we can move on. If no questions, we can move on. Right. Listen. Right, next idea. Listen, now in this part, we are going to draw some wavefronts, right? Basically, we are going to draw some wavefronts, right? Wavefronts are coming from wave phenomena, right? So we know what wavefronts are, right? We had two types of wavefronts. There's plane wavefronts and circular wavefronts, right? And the gap between two consecutive wavefronts is always equal to lambda, equal to wavelength, right? So I'm going to carry that idea forward, right? I'm going to carry that idea forward for the next part, right? Now, the thing is this, listen. Now from Doppler's effect, right? We know it is all about a changing frequency. Doppler's effect is all about changing frequency. That is about a frequency, right? But we know since V equals F lambda, when frequency changes, right? When frequency changes, there is another one who should change, right? That is obviously lambda, because we know V equals F lambda. See, since V equals F lambda, V is a constant. V is a constant to the R, right? If other conditions are unchanged, we know what are the other factors. What are the other factors which V depends on? That is temperature, pressure, and density, right? Because V equals root gamma POM and gamma PO rho, right? We know these equations now, right? If other conditions are same, velocity of sound through air is same. Velocity of sound through air is same. And when other conditions are same, velocity of sound through air is same. That's a constant, right? Then what happens is, when F changes, right, lambda also changes, right? Then what's the behavior? Therefore, frequency and lambda are always inverse. Frequency and lambda are always inverse. Higher the frequency, lesser the lambda, right? Higher the frequency, lesser the lambda, lesser the frequency, higher the lambda. And when we draw wavefronts, right? When we draw wavefronts, we know distance between two consecutive wavefronts is lambda. Now we have to do these changes accordingly in the wavefront, and we are going to draw some diagrams. Right? Take this out. Take this out. Right? Write down below with the red pen. Write down below with the red pen. With the red pen. Write down below with the red pen. Velocity of sound through air remains unchanged. Velocity of sound through air remains unchanged. Velocity of sound through air. Velocity of sound through air. Velocity of sound through air remains unchanged. 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 Remains unchanged. When all other conditions, 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 within brackets, temperature, pressure, density, within brackets, temperature, pressure, and density, temperature, pressure, and density. When all other conditions, when all other conditions remain unchanged, when all other conditions remain unchanged. Right away. Right, as the next heading, take down, next heading. Next heading, behavior of wavefronts. Next heading, behavior of wavefronts. Behavior of wavefronts with Mach number. 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 area of wave runs with map number, right? Number one, find out when map number equals 0. When map number equals 0, what's the meaning? If map number is 0, what about the velocity of object? If map number equals 0, what about the velocity of object? Map number is velocity of object over velocity of sound through air. Velocity of object over velocity of sound through air. Then, if map number becomes 0, which means velocity of object should be 0. It must be 0. Right? Velocity of object must be 0. Then, object is at rest. If map number is 0, object is at rest. Right, listen. As an example, as an sample object, right, I'll be taking an aeroplane. Right, this is the object. Now, from the aeroplane, the sound waves are emitted. Right, from the aeroplane. Assume from the center of the aeroplane, sound waves are emitted. Right. Now, this is the first sound wave it has emitted. This is the first sound wave it has emitted. Right. Sound waves are propagating in all 360 directions. Right. Then the propagation is either circular or spherical. Propagation is either circular or spherical. Right. So that is what I have drawn here. That is what I have drawn here. Right. Now, say another sound wave like this. If there is at rest, listen, if there is at rest, right? If there is at rest, there's no movement, there's no motion of these air particles, right? If there's no change in velocity, if there's no change in velocity, no Doppler's effect. If there's no Doppler's effect, no change in frequency. If there's no change in frequency, no change in lambda, right? Then with same lambda, these sound waves are propagated like this. With same lambda, right? Now, if I mark lambda here, it should be same. Right? Say this emitted frequency is f. Say this emitted frequency is f. Right? This lambda should be same. Right? Because there's no Doppler's effect here. Right? There's no Doppler's effect because source is not moving. Source is not moving. Right? Take down. So likewise, you will be drawing four scenarios. These are three wave fronts. This is the initial wave front. The most furthest one is the first wave front. Because wave fronts are propagating from here. Propagation mechanism, they are propagating from here. Propagating from here. Then the furthest one is the first one. Right? Take down. Right, finished? Right. Then number two, scenario two, when Mach number is less than 1. Scenario two, when Mach number less than 1. When Mach number less than 1. When Mach number less than 1. Mach number less than 1 means velocity of object is less than velocity of sound. Within brackets. Within brackets. Velocity of object is less than velocity of sound. Is less than velocity of sound. Right. Look at now. Present. Is the idea. Present. Now same object. Right. Same object. I mean it's a frequency here. I mean it's a frequency here. Now this travels with the velocity. Right. Let's say that velocity is u. Say that velocity is u. Right. Present now. If an observer is hearing this from this side. Right. Now link this with the previously proved scenarios. If an observer is hearing this from this side. Right. If an observer is hearing this from this side. What happens is the plane is the source is coming towards the observer. When it comes towards the observer, right, the observer is going to hear a higher loudness and a higher frequency. Towards the observer, higher loudness and a higher frequency, which means in this side, observers at this side are going to hear higher frequency. Higher frequencies means lesser lambda. And with respect to an observer here, right, this source is moving away. When it moves away from this one, right, when it moves away from the observer, it is going to hear a lesser frequency. Lesser frequency, lesser loudness. Lesser frequency means higher lambda. Then this side, less frequency but higher lambda. Right? Now what happens is this. Listen. Now what happens is this. Now this is one of the sound waves emitted, right? Wavefronts emitted. And towards this side, lambda decreases. Towards this side, lambda decreases. And towards the opposite side, lambda increases. Can you see? Towards the side here, lambda decreases. And towards here, lambda increases. Is it clear? Right? Wavefronts. In your diagram, it should be clear that lambda is lesser here and lambda is higher here. Right? Write down, say this is lambda 1 and lambda 2. Should be 100% clear that these two are different. Lambda 2, then lambda 2 is less than lambda 1. Write out. Right? Scenario 3, when Mach number equals 1. Scenario 3, when Mach number equals 1. Scenario 3, when Mach number equals 1. When Mn, Mach number equals 1. What's the meaning? Velocity of object is equal to velocity of sound. Within brackets, velocity of object is equal to velocity of sound. Velocity of object is equal to velocity of sound. Right. If Mach number equals 1, is Doppler's effect and Doppler's equation is applicable? Is it applicable? If Mach number equals 1, yes or no? Listen, now this emits a frequency. This emits a frequency, right? But plane is, or the object source is also moving with the same velocity of sound, right? So when it travels forward with the same velocity of sound, say u, right? Now let's say first wave is emitted from here, right? And if we consider the next wave, right? The emission of the next wave, the aeroplane is also at the same point because both are traveling forward with the same velocity. Then what happens is this becomes the same point. Right? Because at any given time, the front end of the source and the sound wave is at the same point because both travels forward with the same velocity. Right? Take down. And for this case, Doppler's effect is not applicable. That is number 3. For that case, Doppler's effect is not applicable. Number 4, when Mach number is greater than 1. Number 4, when Mach number is greater than 1. Right, meaning velocity of object is greater than velocity of sound. Velocity of object is greater than velocity of sound. Right, Mach number greater than 1. Right, now still Doppler's effect is not applicable. Mach number is greater than 1. Right, now the plane is source is traveling like this, it's traveling like this. Say the velocity u, emitting the frequency f, right? Now velocity of the plane, velocity of the source is greater than, velocity of the source is greater than, velocity of the source is greater than velocity of sound. Then sound waves are behind, and the object is always going to be in front. Sound waves are behind now, and the object is going to be in front because velocity of the plane is greater, right? Then it is already overtaken. It has already overtaken the sound velocity or the sound waves, right? Since it has already overtaken the sound waves. Sound waves are behind now, right? Now, if the first sound wave is like this, right? Second sound wave is something like this, right? Third one, something like this. Fourth, like this. Fifth, like this. So likewise, that's how these sound waves are. And it creates a shape of a cone. Right? And in this jargon, we call this a Mach cone. Right? We call this a Mach cone. Right? Take down and label this as Mach cone. Mach cone. Write down. Right. Okay, let's move on. Write down below with a red pen. Write down below with a red pen. Doppler's effect. Doppler's effect is applicable only for. Write down below. Doppler's effect is applicable only for. Doppler's effect is applicable only for. Doppler's effect is applicable only for. Doppler's effect is applicable. Doppler's effect is applicable only for. Doppler's effect is applicable only for. Only for. Scenarios 1 and 2. Only for scenarios 1 and 2. Only for scenarios 1 and 2. Since Mach number is less than 1. Only for scenarios 1 and 2 since. Only for scenarios 1 and 2 since Mach number is. Since Mach number is less than 1. Since Mach number is less than 1. Since Mach number is less than 1. Next point. Keep using red. Next point. Keep using red. When source travels towards. When source travels towards. When source travels towards an observer. 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 Frequency increases. Frequency increases. Lambda decreases. Frequency increases. Wavelength decreases. Frequency increases. Wavelength decreases. Frequency increases. Wavelength decreases. Due to Doppler's effect. Due to Doppler's effect. Due to Doppler's effect. Next point. Next point. Next point. When source travels. when source travels, next point, when source travels, when source travels away from an observer, 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 frequency decreases and wavelength increases. Frequency decreases. Frequency decreases and wavelength. Frequency decreases and wavelength increases. Frequency decreases and wavelength increases due to Doppler's effect. Right. Next topic. Next topic. Mach cone and Mach angle. 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 Right. Listen. So we know Mach cone is always when, right? Mach cone is always when. Mach cone is always when the velocity of sound, velocity of object is greater than velocity of sound. Right now, we consider a similar scenario. If we consider a similar scenario like this, right? If we consider a similar scenario like this, right? Now say this travels with the velocity. Say this travels with the velocity u in this direction, with the velocity u in this direction, and the Mach cone is here, right? And the Mach cone is created like this. Mach cone is created like this, right? Listen now. Now for the ease of understanding, if we draw a symmetric line of the cone, right? See, symmetric line of the cone, right? We have an angle here. We have an angle here, half vertex angle of this cone, right? Half vertex angle of this cone. This angle is called Mach angle, right? Half vertex angle of Mach cone is called Mach angle. Listen. Now, we are going to prove something. Listen carefully. We are going to prove something. Let's assume this sound wave, right? Let's assume this sound wave has emitted. This sound wave has emitted when time equals 0 at this point. When time equals 0 at this point, when this sound wave is emitted, right? Say this is when time equals 0, t equals 0. This sound wave is emitted, right? Now from t equals 0 to equals t, that sound wave travels, no? It propagates. From t equals 0 to equals t, that sound wave propagates. Then it has propagated from this point to here, isn't it? It has propagated from this point to here during this time, from t equals 0 to t equals t. And during the same time, now when this emits, our plane was here, source was here, right? And during the same time, from t equals 0 to equals t, now plane has traveled, right? Plane has traveled, source has traveled from this point to somewhere here, right? Say t equals t again, right? Doesn't now, distance traveled by the plane by the source during this time is, listen, distance traveled by this one during this time is here. Let me mark it here. Distance traveled by the plane during this time is from here to here. Say this is displacement of source, right? Displacement of source, the object here, displacement of object from here to here. That is exactly equivalent to his height of the cone. And this one here, this is the displacement of the sound wave, right? Say displacement of sound SS from here to here, right? And this angle is a right angle. This is a right angle. Now, listen. Using this diagram, I have a clear diagram when you take it down. No? Using this diagram, now I'm going to write tan alpha. See, we can write tan alpha like this. Tan alpha. Tan alpha can be written as, listen, tan alpha can be written as opposite side SS, opposite side S over adjacent side SO. Right? We know, but we know S equals UD. S equals UD. Expand this. Then tan alpha equals, right, SS. If velocity of sound is, let's say V, if velocity of sound is V, then this is Vd. If velocity of sound is V, this is Vt. If velocity of object is U, this is Ud. V cancels. Right? V cancels. Then tan alpha equals V over U. Right? But we know, right? But we know, Mach number equals velocity of object or velocity of sound. Mach number equals velocity of object or velocity of sound. Right? Then this is V over U. Mach number is U over V. Then this is 1 over Mach number. This is 1 over Mach number. Then tan alpha equals 3. Tan alpha equals, right? Then 1 over U over V. 1 over U over V. U over V is Mach number, which means tan alpha equals 1 over Mach number. Right? Tan alpha equals 1 over Mach number. See, tan alpha equals 1 over Mach number. Listen. Oh, sorry. No, tan alpha, it should be sin alpha. I have marked the wrong angle. Wait. 1 second. 1 second. I have marked the wrong angle. Right? I have marked the wrong angle. Listen. Now, this wave front to, if we connect this up, wave front to, this side is perpendicular. Then write sin alpha. Sin alpha. Sin alpha is opposite side SS over hypotenuse. Right? SS over hypotenuse. Let me mark it here. Listen. Then over hypotenuse in SS. Right? SS over SO. Right? Then that is not tan alpha, that is sin alpha. Sin alpha, sin alpha, sin alpha. Then sin alpha equals 1 over Mach number. Right? This is the proved equation. For Mach number and Mach angle. And always we can write Mach angle as 1 over Mach number, or other way, Mach number as 1 over Mach angle, sin angle over Mach angle. Right? Take down the diagram and first do the proof. Take down the diagram and first do the proof. And it's easier when you can think of this cone three-dimensionally, right? Think of this cone three-dimensionally. Right. The relationship between Mach number and Mach angle. The relationship between Mach number and Mach angle. Mach number and Mach angle. Right. And introduce alpha here. Introduce alpha here. Mach angle. Alpha. Introduce alpha. Mach angle. Introduce alpha. Mach angle. Right. So we have only one equation in Doppler's effect, right? Only one equation. That's the main equation. All questions are given. And other than that, this is a good equation. Keep this in mind, right? Right. Any other equations we have proved for those scenarios, those 7 scenarios we proved. No need to memorize. No need to recall, right? Main equation right? General equation of Doppler's effect, right? Finish. Right. Next heading right below. Next heading. Sonic boom. Sonic boom. Sometimes you might have heard sonic boom. Write down sonic boom. Heading. Sonic boom. Write down the heading. Sonic boom. Sonic boom. Right, listen. I will show you a simulation also. Right? If you haven't seen the sonic boom or if you haven't heard the sonic boom, for the better understanding, we'll show you a simulation also. Right? Sonic boom is something like this. When an object travels with a velocity higher than velocity of sound, right? With a velocity higher than velocity of sound, this happens, no? Right? The Mach cone is created, right? When the Mach cone is created, when these wave fronts uh, overlap each other, when they collide each other, they explode because they have a very high energy. They have a massive energy. Right? Since they have a massive energy, right? When they collide each other, it explodes, right? It explodes, and we can hear an explosion. That effect is called sonic boom. Right? That effect is called sonic boom. Not only in aeroplanes. Now, usually we have that in aeroplanes because when it comes to super aircrafts, what we call the superjets, right? Superjets, so uh, high speed jets, right? That is there when it comes to superjets. And other than that, in Perahara ceremonies, have you seen what is going at the very front in a Perahara ceremony? What is it? What do we call it? Ah, in any kind of a parade ceremony, there are something which is like going in the front before the rest of the teams come. If right? Now, when the big piece collided also, right? What happens is there are two strings at the end of the whip, right? So when it is what we call the strike like this, when it is strike to the whip like this, right? Then these two ends, these strings at the ends are going to get a velocity higher than velocity of sound in air. Then when they collide, right, we can hear an explosion, right? That's why the whip sounds uh, in a kind of a very with the high loudness, very high loudness, right? With of course sonic boom down, right down below the sonic boom, right down below the sonic boom. The sound of explosion, the sound of explosion, right off, the sound of explosion, the sound of explosion, the sound of explosion associated with the sound of explosion associated with shock waves, the sound of explosion associated with shock waves associated with shock waves, the sound of explosion associated with shock waves created, shock waves created, shock waves created when an object, shock waves created when an object travels through air, when an object travels through air, when an object travels through air with a velocity greater than, when an object travels through air with a velocity greater than, 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 velocity of sound in air, with a velocity greater than velocity of sound in air, with a velocity greater than velocity of sound in air, with a velocity greater than velocity of sound in air, with a velocity greater than velocity of sound in air. Within brackets, Mach number greater than 1. Within brackets, Mach number greater than 1. Mach number greater than 1. Right? Mach number greater than 1. Right. Mention few examples. Mention few examples. Right? First one. Whip. Right. Then supersonic jets. Supersonic for high speeds. High speed jets. Right? Mention examples. Supersonic jets. Oh, it means, you know, right? People and such and I'll show you how this happens in a jet. Right. And before the simulation, listen, before the simulation, now with this, we have come to the 100% completion of all theories in Doppler's effect. Right. This is the 100% completion of all theories. This is the 100% completion of all theories. 100% completion of all theory parts. All the theory parts in Doppler's effect. Right. So today I finished all the theories in Doppler's effect because when we start applications next day, right? We didn't do any sort of an application today, right? Just only some practice questions, practice occasions, right? Otherwise, we didn't do any sort of applications today, right? When we start applications next day, right? Using a single day, on the single day, we can finish all the type of applications and we can we can finish off Doppler's effect, right? So next day plan is we'll be doing all the types of applications and going to finish off Doppler's effect, right? Going to finish off Doppler's effect after finishing all the types of applications, right? Now, about the sonic boom, it's like this. Sonic boom is something like this. Listen. Right. Once again. Right. See. Sonic boom is something like this. Right. See. See now this one, the shock waves are also visible. See here, shock waves are also visible. Right, that's called the sonic boom. That's called the sonic boom. Listen. That's called the sonic boom. Right. Right. Okay then. Sonic boom and VP is also an example. VP is also an example for this. Right. VP is also an example for this. Right. ඉප්පකට බාන්න slow motion video එක බාන්න එතකොට page things කොහොමද collide වෙන්නේ කියලා. So when they collide each other, it creates this shock wave. Right. So now we are come to the end of 100% completion of the theories of Doppler's effect, and we have come to the end of the session today. Right. So next day will be a full day with applications of Doppler's effect. Go through all the things we have covered so far, because right, we are only doing equations and everything is going to be depending on these ones. Right. Doppler's effect කියලා කියන පොඩි කාලක් මම කියවනේ. Right. By next day we are going to finish this. By next day we are going to finish this. Right. So go through everything and familiar yourself and join the next class. Right. Any questions before we wind up? Or is everything clear for today? Raise your hand if everything is clear. And ask if any questions, if anything, before we wind up. Ask if anything before we wind up. All clear. Right. Then if everything is clear, I will stop for today. Right, we'll stop for today. Right. Then stay there and work hard. And after, I told you this already, after finishing the paper class stuff for 26 batch next month, this month, this month, I'll be starting the graded papers and rank papers for your batch also, right? We'll share all the updates in next classes and through the groups and channels also, right? So prepare yourself to write graded papers, right? Because they will be graded, you'll be ranked, right? And for that, improve your knowledge, prepare yourself, right? All right, then stay there and work hard. We'll stop for today. See you in the next class. Good night and goodbye. See you.